Hey everyone, welcome to week 3 where we're going to be having a look at time dilation with a focus on relativistic time, proper time, and something called the Lorentz factor. So we have quite a number of goals for today's lesson, but today's lesson really extends for the entire week. So we're looking at consequences of the constant speed of light in a vacuum, defining some new terms of time dilation and proper time interval, describing time dilation, including experimental evidence, and obviously we're going to be able to solve some problems at the end of today's lesson as well. But before we get into that, let's start with a warm-up. So we have a diagram here on the left with two rockets traveling 0.25 c in opposite directions. They pass each other at the instance that they receive a light pulse from a distant star. Observers on both rockets attempt to measure the speed of light from this star. So it's your job now to determine the speed of light according to both rocket 1 and rocket 2, according to Galilean relativity and special relativity. So pause this now and have a go at that. All right, so according to Galilean relativity, remember which is our classical physics, our spaceship here flying towards the pulsar is going to perceive that as higher than the speed of light, or in fact 1.25 c. Obviously that isn't true according to Einstein's postulates, but according to Galilean relativity, that's what it would perceive it as. Whereas this spaceship here travelling away from it would only see it as 3/4 of the speed of light, or 0.75 c, according to Galilean relativity. According to special relativity though, guys, hopefully you recall Einstein's postulates there, and in fact they will both simply see it travelling at c. Look at that, there you go. All right, let's move on. So we're going to get into time dilation, and for the next couple of minutes we're going to be doing a bit of a derivation. Now this derivation is not going to be expected of you to do under examination conditions. It's just a really nice mathematical proof of why time dilation is a phenomenon. So let's consider this. We have a really high moving train with Fred sitting on the train, and there's a light pulse travelling between this mirror and this mirror. Say this train is travelling close to the speed of light. We then have a stationary observer over here, Pierre. So he's standing at the side of the track and he sees the train in motion. Now, from Fred's view, the light travels a distance w here, okay, backwards and forwards, and he can time, so these are their stopwatches, he can time how long it takes the light to travel up and back. According to Fred's view, the light travels simply up and back in a straight direction. So since we know that distance equals velocity times time, and this is a light beam, so he knows that it's travelling at c, and the time that he measures is t0 on 2. Now we're giving Fred a special naught there because he's in the reference frame where the event is happening, and we'll come back to that later. If we now consider Pierre's view, so Pierre's over here, because the train is moving so fast, he actually sees the beam sort of travel in a bit of a triangle. All right, now he agrees that the total width of this triangle is the same. Okay, it's still traveling from mirror 1 to mirror 2, but he disagrees with a couple of other things. He notices here, yeah, okay, sure, the velocity is the same at c, but he's going to disagree on the time. So we're going to call Pierre's time just t here, and it obviously takes half the time just to get from one mirror to the other, hence the t on 2. We also notice that there's a time that it takes to travel in the horizontal direction, which is based on the velocity v of the cart. So that's distance that it travels, or distance that the light travels in the horizontal direction, is going to be the velocity of the cart times the time, which in this case is half the total measured time, since we're only travelling from one side to the other. So I'm going to go to a new slide now, and I'm going to do a little bit of a derivation of how we can equate what Fred sees and what Pierre sees in terms of time. Okay, so this is our situation. We have Fred saying that the width is CT naught on 2, and we have Pierre that agrees on the width, but he thinks that the distance that the light is travelling is actually a little bit different. So if I'm going to work with Pierre's expression of width for a moment, it's actually just an example of Pythagoras' theorem. Okay, so Pierre will say that the width or the vertical distance that the light travels is the square root of CT on 2 all squared minus VT on 2 all squared. And now here's the cool thing about this, guys, is we now have an agreement of that vertical distance that the light has travelled, okay? So we're going to now equate these two positions from Fred and Pierre's reference frames. All right, so CT naught on 2 must be equal to the square root of CT on 2 squared minus VT on 2 squared. Okay, so that must be true because they both agree on that width there. Our job now is to work this equation so that we have T, the time measured in Pierre's view, as a function of T naught, the time measured in Fred's view. Okay, if you would like to, as an exercise, pause this now and have a go at that yourself. Otherwise, follow along with me. We're going to work the right-hand side for a moment. Okay, we're going to bring that, simplify it a little bit by bringing that squared down into those brackets. So we end up with C squared T squared on 4, take V squared T squared on 4. And we notice here that we have a common factor of T squared all over 4. So we're going to take that out the front. Okay, so working that right-hand side still, T squared on 4 outside of C squared minus V squared, all under the square root sign. We can now apply our third rules here, okay? Oh, running out of space a little bit. We might start up on the other side. Okay, so working that through here, we end up with CT naught on 2 is equal to the square root of T squared on 4 times the square root of C squared minus V squared. Okay, so in other words, CT naught on 2 is equal to T on 2. So we're getting a little bit closer to representing T as a function of T naught there. So our 2's are going to cancel out there. And I'm going to do a quick rearrangement of T as a function of. Okay, so I'm going to make T my subject. Get that blue pen back. So in other words, T is going to be equal to CT naught divided by C squared minus V squared. All right, so this is where we're at right now. So at the moment, this looks a bit messy though. We're not really happy with the C on top and a C on the bottom, so we want to make sure all of our C's are together. So I'm now going to express my C on the numerator as a third. I'm going to call that C squared square rooted. Okay, so this is now my situation. I'm going to continue up the top here. Sorry for my working going all over the place there. I'm now, with my third rules, able to bring that entire thing into a single third. So it's going to look something like this. I'm going to bring my T naught out the front, okay, and I'm going to end up with C squared over C squared minus V squared. All right. Now, I'm not going to do anything particularly special, but what I am going to do is I'm still not happy that I've got now a C squared on the numerator and a C squared on the denominator all under a third sign. That's not ideal. So I'm going to do to the top what I do to the bottom in my fraction. So I don't actually change my fraction. I just change what it looks like a little bit. And I'm going to divide both the numerator and the denominator by C squared. That's not changing my equation. It's just working with my equation. So we now end up with, on the numerator, we have 1 over 1 minus V squared on C squared. And if we want to write that in a really nice way, Okay, that's equal to T naught over 1 minus V squared on C squared. Let's just fix that C up, it's a bit gross. Now, if we go back to where we were before, we were considering Fred and Pierre on the train. What this means is we now have an expression of T in terms of T naught, so an expression of what Pierre measures in terms of what Fred measures when it comes to time. We say that what Pierre is measuring is called relativistic time because he is seeing a relativistic effect because the train is travelling so fast. Where T naught, the time that Fred is measuring, is proper time because Fred is in the reference frame of the event. So let's evaluate, or rather let's define those variables a bit more specifically. Proper time, also called the proper time interval, is the time interval measured in the frame of reference which the event is occurring. So that was Fred. And relativistic time, or the relativistic time interval, is the time interval measured in the frame of reference in which the object or event is in motion. And just a little bit of a note here, that relativistic time is always dilated. So that's why we call this time dilation. In other words, relativistic time is always going to be longer than the proper time. So just before we get into working with some examples, there's one key part of this formula we need to look at. And that's this guy here in purple, known as the Lorentz factor. That Lorentz factor, which is really just to do with the speed of light and the speed of the event in the moving frame of reference, okay? We call that Lorentz factor gamma. So if we really wanted to make our life a bit simpler, we could represent time dilation or relativistic time as T naught times gamma. And we're going to explore the Lorentz factor just a little bit now for the next minute or two because we're going to see it again next week when we talk about space or length contraction. Because remember, special relativity doesn't just affect time, it affects space as well. So, the Lorentz factor is simply the 1 over root 1 minus V squared on C squared part of our time dilation formula. And what's really interesting to note is that depending on the velocity that you're actually travelling at, you notice that the Lorentz factor is really close to 1. So the closer this value is to 1, okay, that means that we're not really seeing a significant effect of time dilation at all. So you see here, even when we're travelling at 3 by 10 to the 5 metres per second, we're really not seeing any time dilation. This is an insanely high speed if we're to consider it in real life, but not when it comes to time dilation effects. In fact, it's not really until here, 1.5 by 10 to the 8 metres per second, which is half the speed of light, that we actually begin seeing some significant effects of special relativity. If I was to put that in a graph, I want to see how gamma changes as V is a function of C. So it's not really until here at 0.5 the speed of light that I'm actually seeing this factor over here be anything significant or anything greater than 1. But you do see we have this insane exponential growth, and in other words, the Lorentz factor is really playing a role at these really high speeds close to the speed of light. So that's just something to keep in mind. So let's get to our experimental evidence. In our first lesson, we discussed muons, and we discussed how, they have a mean lifetime of about 2.2 microseconds, and they're traveling super fast, basically at the speed of light. We stated that, according to their mean lifetime, they should be decaying at about 660 meters. But we observe heaps of them about 15 kilometers after they enter the Earth's atmosphere, which is at the Earth's surface. So what we're going to do now is we're going to do a quick little calculation. If, for example, I consider for a moment that we're actually observing those muons moving. We're actually observing a relativistic time or a time dilation. If I consider that the proper time of the muon is the 2.2 microseconds because the event is the muon moving, okay? And we're also going to consider that, you know what, 0.999c is really close to the speed of light, but it's not the speed of light. Our Lorentz factor is going to play a pretty big role here. All right, now if we pop all of that into our calculator, it turns out that the relativistic time that we observe is that the muons are actually staying alive for 49.2 microseconds. And that agrees with what we actually observe. Next week, we're going to talk about how that time dilation observation explains why they actually live for so long as well. So this is a piece of experimental evidence of special relativity and time dilation. With that, we've got 2 questions here from your textbook. In each of these examples, you have a velocity very close to the speed of light, and you need to calculate the relativistic time in each case. Please have a go at these now. All right, I'm not going to work through those examples, guys, as it's very similar to what we saw here, where we're just substituting in our value for v and our value for proper time. For the first question, you should end up with 5.42 seconds as your relativistic time, and your dilated time for the second question is 520 seconds. So with that, you're now able to answer the questions in the textbook review 10 in chapter 10.5. If you have any questions at all, do not hesitate to contact your teacher and make sure you're